Here's an example that shows fixed point of an equation. So in this case, what would be a solution and a fixed point of this function? Okay. After doing some high school mathematics, we can draw this kind of graph, and we will come to know there are two fixed points of this function, this one and this one. Okay. Then the small one will be the least fixed point of this function, and the larger one will be the greatest fixed point of the function. Okay. Next, let's do some more exercise for you to get more familiar with this fixed point style definition. Here is a more CS style example. Here is an equation that describes a certain set n. The set n is constructed like this. So an element of this set n is either 0 or a successor of an existing element n. Okay, intuitively, what does this n mean? So this set represents a set of natural numbers, as you can guess. Okay, then let's define this set using a fixed point style formalization, because this one is actually an equation, as you can see. On the left hand side, n appears here and also appears on the right hand side. So it is not an explicit definition. So if we introduce a function f that comes from that inductive definition of n here, okay, then what happens? So n is actually a fixed point of this f, especially the least fixed point of this f. Okay. Here, as you can see, I don't do anything special. I just replace this n with x. Okay, as you can see, and then I just introduce function f. Okay, here nothing special. Okay, then formally we can define n like this. N is the least fixed point of this function. Okay, here, as some of you may guess, there are multiple fixed points for this equation. For example, the set of natural numbers is one possibility, and the set of rational numbers is also another possibility, and so on and so forth. There are many possible solutions. But in this case, what is the least and compact representation that satisfies this equation, which is natural numbers? So that is what we want to find. A similar example is here. So here, an element of set L is either a constant element called nil, or an element that is made by prepending 0 to an element of L. Okay, intuitively, what is this set? This is an infinite set of lists of 0. Okay, let me show you the set. Okay, so nil can be one element, or if you append 0 to nil, then that will be another element. Also, you can append 0, another 0, and so on and so forth. Okay, this is an infinite set of list of zeros. Okay, then let's define this set L using fixed point style formalization. So as before, we can rewrite this equation, okay, by introducing a function f, and just replace this L and L with a variable x. Then what is L? Okay, L is a least fixed point of this f, which is a solution of this equation. Okay, especially, yeah, as you can see, there are multiple possibilities for the solutions of this equation, but we are interested in only the least fixed point of the function. Okay, a bit more complicated example here. Now our target is not just a set, but a function. In this case, a function rich. Okay, recall that the semantics of while. Okay, the semantics of while was also a function, not just a simple set. Okay. For this example, what does that mean intuitively? This reach represents a set of nodes that are reachable from a given set of node n via this next relation. Okay, suppose we have a given set of node and there are many edge relations like this. Okay, suppose n represent only this part, and also there can be some loops here. Okay, intuitively this reach n means all reachable nodes from this set of n. Okay, then possibly the output will be this set of nodes. Okay, then let's define this reach function using fixed point. First, let me rewrite reach using the lambda notation. Okay, and then what is reach? Once I replace this reach with x, okay, then reach is a fixed point of this function f. Okay, all are the same as before. Okay, then finally we can define reach as the least fixed point of this function. Okay, the last example is also similar. It's a common factorial function. So let me do the same thing again. So let me first rewrite the function definition using the lambda notation. Nothing special here. And then I replace this fact with x, okay, and introduce this function. Then what is fact mean? Fact means the least fixed point of the function f. Okay. So, okay, I believe now you get much more familiar with the concept of fixed point. So from now on, let's think about more theoretical questions about fixed point. For example, why does the semantic equation always have a solution? And does the equation have a unique solution? Or how to compute the solution in practice? Okay. These kinds of questions are answered by a theory called domain theory. So according to domain theory, the semantics of program is an element of a domain called CPO. That means complete partial order set. We will learn what CPO means in the rest of the lecture. For example, here the semantics of program command is an element of a function domain from memories to memories. Okay, and the memory space is also a domain. Okay, the semantics of program is the least fixed point of a continuous function. We will learn what continuous function means in the rest of the lecture. Here, for example, as we defined the semantics of program, here semantics of while, for example, is the least fixed point of a continuous function f. This f will be a continuous function. Okay. This theory was established by early computer scientist named Dana Scott. So if you are interested in the details of the theory, I recommend to read these following seminar papers. Okay, throughout this lecture, let me summarize the essence of domain theory. So here we can start with the basic concept, which is partial order and partial ordered set. So a binary relation here, that intuitively it means less than or equal to, which is a partial order on a set D. Okay, if it satisfies these following three conditions. Let me take a look at this one by one. So for all element A in the set, so if A is always less than equals to itself, we say that this condition is reflexivity. Okay, or the second condition means anti-symmetry. If A is less than or equal to B, some element B, and at the same time B is less than or equals to A, then it means A is actually B. Okay, that means anti-symmetry. That means that this relation is not symmetric. Okay. The last one is transitivity, which means that if A is less than or equals to B and B is less than or equals to C, then it implies A is finally less than or equals to C. Okay. Then this set D with a partial order, this relation is called a partially ordered set. We will use this notation, or simply we call this poset. Okay. Actually, this partially ordered set is not a very new concept for you. Many sets you are already familiar with are actually partial ordered. Okay, here are some simple examples. So let's take a look at these examples one by one. So first one is the power set of a set X, Y, Z with the standard subset relation. We use this notation to represent power set. Okay, so this is a partial order set because, okay, let me show you this graph. Here each circle represents an element in the partial order set and each edge means the order. Okay, for example, the empty set, okay, is less than, the less than means subset of, okay, less than the singleton set of Z, and this singleton set of Z is less than the set of YZ. And then finally this empty set is less than the set YZ, okay, according to the subset relation. That is for the transitivity relation, transitivity condition. Okay, so it is actually a partial order set. The next example is that the set of integers with an additional element called bottom. Here, usually we use this notation to represent the least element of a set, and we call it bottom. On this set, we can define this kind of order relation. Let me show you this graph. So bottom is less than all the other integers, and there is no order relation between integers. Okay, these sets construct very flat structures like this, and it is also a partial order set. The next is the set of natural numbers with the standard order relation on natural numbers. This set will trivially satisfy the previous condition, so it is a partial ordered set. So here, as you can see, it is just simply, we can simply apply this standard order relation. The last example is actually, we can also, it is possible to add the infinity to the natural number set, and we can simply extend the definition of the order such that the infinity is larger than all the other natural numbers. Then finally it will be also a poset.